Everybody. So today we're going to go over understanding the physics of different geometries. And then very specifically what I want to outline and showcase to you is that just simply changing the geometry of an environment changes the physics of it completely. And that's a hard concept to grasp overall because we're used to physics being physics, right? But and it doesn't like that concept doesn't matter to us as humans because our physics will always be our physics, right? We operate in a physical three-dimensional world that is on Earth and bounded by the universe that it is, and all of the rules that are bound by our rules of physics. So to us, and for all intents and purposes, physics to us is bound, right? But there are universes, shapes, etc., that exist that are not our universe. And by exploring those different shapes, they have ramifications on especially things like artificial intelligence, right? Is where it becomes an huge play. And giving you kind of like an upfront insight as to why exactly you would want to understand, control, and essentially master these different geometries of these different spaces is that once you understand it, you can take advantage of it. So very specifically, for example, I understand that if I want to increase entropy within an environment, that different physics have different entropy speed limits, just like there's a speed limit to the speed of light, right? And then what we have shown, if you aren't aware, is that that speed limit can be slowed down, right? Like physicists have now at the point they've literally like frozen light is the latest step that they've been able to take it, slow it down to literally zero. And then within that, there's a speed limit of light within our universe. But again, there's nothing that controls that speed limit less than that. And it's the same thing with entropy, right? And then so in digital spaces, and I've shown this time and time again, I can control the flow of the entropy within the digital space, either make it faster, slower, etc. And then part of that lever is specifically pulling on geometry. It's geometry plus resonance, right? And then those two levers combined allow you to do a lot of very interesting and unique things in digital environments that you wouldn't think that you'll be able to do. Right? And then so very specifically, the environments that we're going to be looking at today are Euclidean, hyperbolic, spherical, and fractal. And then just giving you kind of definitions if you aren't aware of these particular spaces. So Euclidean space is unbounded space, unbounded mathematical space, right? Infinite. There's no box. There's no dimensions to it. It just is, right? And then it's from 0 to infinity, and there's no zero. It's just infinity. And then within hyperbolic space, it's like that same type of space, but there's a curvature. We literally curve the space, and we curve space itself within that, right? And we put a curve, not a sphere. It doesn't create a sphere. It's just a curve in the space, a curve in space-time in that, right? And then so that has ramifications on the geometry there, and very specifically pay important and pay special attention to, and I'll point it out a few times, to hyperbolic space, because in some instances you'd be like, man, hyperbolic space operates exactly like Euclidean space, and then in other instances you'd be like, man, hyperbolic space operates almost exactly like spherical space. But what you're going to notice is that it's going to shift between those two, and that's what's interesting about it, right? And then we have spherical space, which is like a 3D circle. And then fractal space, which is like so just space folding in on itself, like it just manifold folds, right? Is like the best definition of fractal in this instance. And then so we're going to perform 8 different experiments, and then when in every single one of these experiments, all I do is code the geometry, right? We code the different geometries, and then we observe the interactions that occur in these different geometries. And I'm going to do different types of physics experiments within these geometries, right? And then so we'll do 8 experiments. And then so again, no physics engine, no rules, just geometry. So everything that you see is an emergent outcome of the space itself. And then so let's dive into it. Experiment number 1 is we're just going to essentially, this is a free motion experiment where geodesics travel across the curved space. And then so here is first Euclidean, And then notice the scale here. So it's going up to 4 and 4.5, right? Which is different than the scale of our hyperbolic space. So I'm noting that, like, while this looks very similar to each other, notice that like spherical and Euclidean and hyperbolic space in this instance have almost the same measurements, right? They're the same scale, whereas Euclidean space has a different scale in this instance. And then fractal is fractal space, right? It's always going to be like the different one, and then very specifically the different one, right? And then so just again the same like all we're doing is changing the environment here, and the geometry of the environment, and it very literally changes what happens within it, right? So experiment 2, we're going to utilize a diffusion experiment, and I think this will make it more crystal clear. So we're going to observe how diffusion patterns differ across geometries. And then so very specifically, what we can see here, here's our Euclidean pattern. And then notice the dots very specifically, and where the dots are at, this hyperbolic pattern is definitively different, right? And then you can see the dots are very different. And then let's notice, and I want to point out and something here very specifically because it is important, right? So if I can zoom, yes, perfect. So if we look at this structure, especially of these dots, right? And then let's go down here to Euclidean dots. What we see and what you can observe very specifically within the hyperbolic space as opposed to the Euclidean space is more instances of clustering is what I want to point out, right? So this compared to this, they're more evenly spread out in this instance, whereas they're more based off of cluster dynamics in this instance. And that's part of the physics that plays a huge part of this and highlighting that. Like if you like drop a bomb in Euclidean space, it's a perfect dispersion, right? Like 100% perfect, like boom, perfect interactions. Whereas if you did the same in a hyperbolic space, it's not perfect. It's not like a perfect circle, right? It's because it's clustering dynamics are far enhanced in hyperbolic space, as you can see here. And spherical space is more radical spreading, right? And extreme uniformity of spreading, but we can see it's and as we'll see with some of these experiments, it's warped in the middle. It would be the best way to visualize that. And then fractal space is again like fractal space is just totally different. And then experiment 3, so this is oscillations and tethering in different geometries. And then so very specifically, how do natural oscillation patterns emerge specifically based off of geometry? So again, only difference that we're doing here is we are changing the geometry. And then so we have particles that are tethered to a central anchor point by a geometric constraint. And so the anchor point here is always in the middle, right? And then so what happens here in these different geometries, so our anchor point of Euclidean compared to hyperbolic. And then in this instance, pointing out again, so in the previous experiments, hyperbolic was very close to spherical, and Euclidean was very different than those two. Whereas in this instance, hyperbolic is almost mirroring spherical, or is almost mirroring Euclidean, right? And there is some very slight difference with these secondary, like, so the anchor is in the middle, right? And then you have like your primary expansion and your secondary expansion. And then if you notice where the secondary expansion starts with Euclidean, it's slightly more spread out than it is in hyperbolic. So they're not exactly the same. But in this instance, Euclidean and hyperbolic look very similar, which is drastically different than spherical, pointing that out, right? Like the anchors, and that's what this like repelling from the center, right, is very clearly illustrated here within a spherical space, and this gives you that perfect illustration, right? So here's that anchor in the very center. You can see like nothing wants to touch it, right? And then so you can see it's this is our 3D, 2D visualization of this like 4D concept, right? And then so this is kind of what that looks like, and it's interesting how it looks. And then fractal is just like who knows what's going on there, right? It's like, okay, it's just cool. And then experiment 4 is collision patterns in different geometries. So we're going to smash particles together, and then how do natural clustering or deflection patterns emerge across geometries within this instance? And then, as I pointed out before, and you want to pay attention to, hyperbolic space tends to increased clustering dynamics, right? But what we see in these environments, and what you will see in these environments, is some of them have the exact opposite effect, where some of them increase deflection dynamics. And then so we're going to just have particles move freely, and then we want them to collide. So we're going to like have them collide in these interactions, and then where they come close, and then we're going to see what happens within them. And then so here's our Euclidean space. Here's hyperbolic. So again, like hyperbolic is a accelerator for some of these things, right? Not all of these things. But in instances where it is, you know it is, like this, for example, right? But in this instance, again, so in the last experiment here, hyperbolic is very close to Euclidean, right? So like this and this are almost the same. This is drastically different. We go here. Here's Euclidean, vastly different. And then here's hyperbolic, here's spherical. Well, they look very similar, right? So again, like, I can't point this out enough. Depending on the experiment, hyperbolic is going to change, right? It's going to be either very close to Euclidean or very close to spherical. And you're going to get observations of both. Hyperbolic is a very unique space within this. I can't point that out enough. And that's what I'm trying to do within this. And then fractal is again like just doing its own thing, right? And then so experiment 5 is field propagation in different geometries. And then so in this observation, how does space geometry warp our wavefront propagation in this instance? So in this instance, we're going to simulate a signal that's radiating outward from a central origin, and it's propagating out. And then so what happens with that signal in the different spaces, very flat out. So here's Euclidean, here's hyperbolic. And then again, they look very similar, but there's repellent in the center of hyperbolic as well. We know, and I've showed you in those previous experiments, that there's definitively like repellent in the center of spherical space. We're seeing that same repellent here, but for the first time in hyperbolic space. So that repellent exists and doesn't exist in hyperbolic space. Again, like hyperbolic space has unique physics characteristics compared to these other spaces, and I can't highlight that enough, right? So here we go, here's hyperbolic compared to spherical. And then in this instance, spherical actually looks really close to Euclidean, but if you notice again, like the scale, like pay attention to the scale of this graph, right? So Euclidean is going up to like 4.5 on almost 5 on this top, it's stopping out at 5 at the scale, right? Whereas the top at spherical is 1 across in either way. And then again, fractals like burp. And then so then we go to experiment number 6, which is entropic flow in different geometries. And then so this observation is, how does entropy unfold in each space without any external forces? So we just put entropy in the environment. Entropy decreases over time, but according to Shannon entropy and diffusion dynamics. But how exactly does that occur within these spaces, right? It has to dissipate somewhere. So we're going to watch exactly how that interaction occurs. So we're going to observe that particles begin in a high density cluster and they're allowed to flow upward from there. And then what happens with that entropy? And then so here's our entropy flow for Euclidean space compared to hyperbolic. So again, we're back to, in this particular experiment, of hyperbolic looking very similar to Euclidean, although what we can see is very different dynamics with regards towards this spread, right? So more, I'd say, uniform spread of and spread mechanics with regards towards this Euclidean space, whereas much more, far more clustered dynamics and more not 100% like uniform with regards towards the spread overall, right? And then spherical, it's the exact like the most uniform spread that you can get, beautifully uniform in this instance for an entropy spread, right? And so very clearly you can see within this particular space, like if you're talking about entropy dynamics and entropy spread, spherical space it has far different physics dynamics than both Euclidean and hyperbolic spaces, pointing that out. So then again, if you do experiments, and especially if you're doing experiments around entropy spread, and then and then here's fractal, right? In either one of these two spaces, in spherical or fractal, and then you make your measurements, you're going to be very thrown off with your measurements as opposed to in hyperbolic and spherical and Euclidean space. And here, like, hopefully this gives you a visualization as to why, right? To me, the hardest part of understanding and grasping these things is the actual visualization. So hopefully this solves that for you, right? We're talking about digital spaces, but these digital spaces have real physics attached to them, as we're seeing here, right? This is a real visualization of this space. So like pretend it's an actual space, and this is the actual physics differences that are occurring, and we're literally observing the differences within these spaces. And then so we have two more experiments. Next is resonance patterns in different geometries. So how geometry structures harmonic zones, interference, and constructive and destructive patterns. So multiple periodic sources emit influence and observe interference and natural resonance patterns within these experiments. Again, mapping out the like real world within this, and like a lot of this. So like people wonder like it seems like so there's advancements around like torque clustering and fluid dynamics, etc., and like all of these things that come into this. They all come into play around this, right? Because you have such different and varying reactions and different effects within the different spaces, right? Like so, like in this Euclidean space here, very specifically, I'm blowing this up again, right? There's holes in this space. Like these are like imagine that this is a data set that the model is training on. There's like black holes in there, like black holes, whirlpools, whatever you want to call these holes that exist. Like these are real in the space, right? And so if you have a cluster and then a model hits one of these holes, like it's going to change the dynamics overall of its learning, and they're in all of these ones, right? But then we go down, and then in like here, no holes in there, right? So if you like inside, and maybe there's a hole there, no holes here. But so I'm highlighting this very specifically that like there's more internal turbulence in this space than there is in this space in this particular experiment, right? And then so again, another experiment, it could be the exact opposite of these, which is why there's no free lunch, right? Like no algorithm performs 100% optimally across all of these geometries. And then so here's spherical, where we have those same effects, right? But we have in spherical, we get it's much broader, right? So we can avoid, if we know how to avoid, we could more easily avoid those bad clusters in Euclidean than we could actually in spherical. And then fractal is actually generally the one that's like the kind of the derpy one. But in this instance, like fractal is the one that's like, I got this, bro. Cool. Like it's here. Like here's exactly what you're looking for. I'm just going to contain it all within this star because I can do that. Like and then like we go to the last experiment here, which is dimensional fold test in different geometries. And then so the observation here is how do space folds, loops, and dimensional structures affect traversal behavior. And then so in this instance, particles attempt to traverse recursive or folded topologies. So they're existing within a manifold itself. Within a lot of architectures are manifold architectures, right? Like for neural networks, brains, things like that. And then so what you can see is that, like things operate weirdly and differently in manifolds, right? Kind of interesting, the dynamics that occur here. This is just straight up agent behavior. And then so agents and manifolds, naturally, here's like massive clustering dynamics as opposed to just uniform spread. As opposed to not as heavy on the clustering dynamics, but very similar. So again, in this instance, in this particular experiment, hyperbolic is back to like essentially simulating a spherical space, and then fractal space is figuring something out here in these last two experiments, right? And in all of the experiments, fractal is just like, oh, doing its own thing, just playing around, burp, burp, burp. And then it's like fractal actually has these last two like more nailed down than the other ones, right? Like fractal's like, yeah, no, I got you, bros. I'm just gonna do that naturally. Like I'm just gonna like compress all of this into some sort of ordered structure naturally. You didn't think it was going to happen and I could do it, but here you go. And then so that's kind of the physics of these different spaces, right? And so like the major thing and the major bottom line, like if you do distance measurements, any sort of measurement whatsoever, it doesn't matter what measurement you're doing, you're going to get a vastly different measurement in this space as opposed to this space depending on the experiment, and then especially if you're doing things like with diffusion, for example, right? If like I run an experiment, if you run your experiment on diffusion in Euclidean space, and then I run it in spherical space, and then I'm like, hey, here's the outcomes of my experiment, and then you reconstruct it, and you reconstruct it in Euclidean space, and you're like, hey, this guy doesn't know what he's talking about, like, or this guy's off, right? I don't get anywhere near the same metrics that he got. Well, like, yeah, like here, like this literally made all the difference in the world, right? It's those simple things, and like all of this goes into making all of this so hard, right? It's chaos theory. Literally every single possible interaction or change that you make within this system, just observing the system changes it's another lever, right? Everything are levers within this. And so understanding that, what you understand is that you don't actually have control over any of these levers. Is the bottom line, right? If you understand how the levers work and you understand the physics of the lever, you get more ability to pull the lever and to adjust the lever, but the levers are going to do their own things, and they're going to do different things, right? And then so that's, to me, the beauty of all of this, and the fascination of the physics of it. To me, like, so this is like cutting edge physics, right? Like there's like very few people that delve into like topological physics within digital spaces overall. So hopefully this gives you something new, cool, unique to reflect on. I'll leave a link to the description of this notebook. It's all MIT licensed, just so there's nothing around that. And if you like this type of content, please like, subscribe. Thank you very much.